In this set of videos, we'll be talking about different ways that the Laplace transform handles what I'll call translation. We're going to start out by just listing all the properties we'll use in this section, and then we'll do just a bunch of examples kind of applying them. And then midway through, we're going to deal with a special kind of like piecewise approach. So let's go ahead and list out all of our favorite translation properties. So I'm going to write all these down, and it's going to seem like a lot, and then we'll go through examples so you can actually implement all of them. But for now, just kind of accept it as it comes. So L of e to at times f of t is going to be capital F times s minus a. And then conversely, L inverse of capital F of s minus a is going to be e to at times f of t. L of f of t times u of t minus a, where u is a special function that we'll define in a second, but that's going to be given by e to at times capital F of s. And so exact opposite, L inverse of e to at capital F of s is going to be, sorry, that should be an s. We should never have s's and t's in the same equation. So it's e to minus as times f of s. That's going to take me back to f of t minus a, u of t minus a. And it's a little crunched, but I think that you all are going to be able to put together that f of t, u of t minus a should be the same over there. And then Laplace of just u of t minus a itself is the case where little f is 1, so capital F is 1 over s. So it's just going to be e to minus as times 1 over s. And all of these were written with the assumption that L of little f is big F and L inverse of big F is little f. That's just the notation we use. And that special function u is what we're going to be talking about in the second half of videos. But just so you have it in one place, I want to write down that it's defined this way. It's 0 until t reaches a. Oh no, I wanted the undo button. Until t reaches a excluded. And then for any t equal to or greater than a, the function is 1. So just have these in a handy place in your notes because you will want to refer back to them to solve a lot of different types of problems. I do want to note that the reason I grouped these together is that these properties are kind of about like shifting solutions sideways along the like horizontal axis of x or s. And that's how they're related. You're thinking about shifting t over by a or thinking about shifting s over by a. We're going to go into our first example of using one of these properties. And I'm going to go to a new page actually because I don't want to run out of space in the middle of it. So if you're still copying down the properties, hit pause. But supposing we want to compute the Laplace transform of e to 5t t cubed, or the Laplace transform of e to minus 2t cosine 4t. These are going to be examples that use the property that says L of e to at times f of t is equal to capital F of s minus a. And this one is our participation problem. Although I've not been noting that with words, in other videos it'll be denoted by stars in the video list. So since we're going to use that property, we need to sort of define what A and little f are so that we can plug in capital F of S minus A. We're going to end up needing, kind of for this first one, my function f seems to be t cubed. So I'm going to go ahead and compute Laplace of t cubed, because that's something I know. 3 factorial over s to the 3 plus 1, or 3 times 2 times 1 over s to the 4, so 6 over s to the 4. That would be capital F of s for little f equal to t cubed. And I guess I should have said that's using that power property for n equals 3. I'll put it here. Sorry, I've been trying to write those down for you all. I hope that you have the properties kind of next to you all the time when you're working on these problems. So then, if I'm looking at my e to 5t times t cubed, then for this problem, I have that a is equal to 5, and I know my little f is t cubed, and my big F is 6 over s to the 4th. So I want to plug in big F of s minus 5 for that a value. So I'm just going to plug in where I see s above s minus 5. And that's it. So we'll do the same thing with the next. For our second example, our f is cosine 4t. So then L of cosine 4t, I know from L of cosine kt is s over s squared plus k squared. So for us, that's going to be the case where k is 4. So it's going to be s over s squared plus 4 squared, or s over s squared plus 16. This is going to be our f of s for the second example. Then when we think about trying to compute L of e to the minus 2t cosine 4t, my little f is cosine, my big F is s over s squared plus 16. I need to know my a, which is minus 2. And then I'm going to plug it into f of s minus a, which is f of s minus minus 2, so plus 2. And then everywhere I see s, I'm going to switch it to s plus 2. And that's it. I do want to note that sometimes you all will be tempted to distribute that s plus 2 squared, like turn it into s squared plus 4s plus 4. In general, you want to leave it looking like this for as long as possible, because then if you just have to undo it, you know that it looks like something you did up above, and it's easier to kind of track where this term came from. So I wouldn't simplify that denominator. I would leave it like this. And then I don't want to I don't want to risk that this video is super long, so we're going to hit pause, and then we'll do another example that deals with the inverse of this in the next video.